As always, my name is Gatebe, it's so simple. And as always, I want to start the Maniac Talk with a story. I grew up in a place, in a village, which is dissected by rivers. And those rivers actually were fed by glaciers coming from Mount Kenya. And this is the second highest mountain in Africa. Now, during the rainy seasons, the streams, those rivers would overflow with a lot of water. And the villagers had difficulties crossing from one village to the other. But one thing was true, and one thing was clear to all of us, that there were places on those rivers where there were stones which were sticking out. And the villagers knew those were the places which were safe to cross the river. So from that, we made parables out of that. And we say that whenever you see an old stone has weathered a lot of things, even storms and even floods. And our grandfathers taught us to watch out for those small stones. So we used to describe those people with a lot of knowledge who have weathered a lot of things with that name, an old stone. So today, ladies and gentlemen, I'm actually very privileged to introduce one of those old stones. Parkinson has been with us for the last 34 years. When she joined Goddard, climate issues were not significant at all. But today, they are bumper sticker issues. She has seen it all. She has done a lot. She has written a lot of books on climate, on sea ice. So whenever I have a question, or whenever we have a question, she is, no doubt, our village stone. An old stone. Let's give her a clap. On leadership, actually, since 1993, she has been at the helm of the Aqua Mission as a project scientist. 1993 to present. She saw the Aqua being launched in 2002, and just this year, we celebrated 10 years because of her leadership. Let's give her a clap because of her good job. Good job. So I actually requested her to come and tell us, how did you get there? An old stone. Well, we can go for advice, like those villagers. So please help me welcome our speaker, Parkinson.
Great introduction, Katabi. Thanks very much. Thank you. Okay, when I was a child, my interest was overwhelmingly in math. I loved the simplicity. I loved the precision. I loved how you could take a problem that sounded so difficult and it would become so simple just by using the appropriate symbolism. So math was overwhelmingly my central intellectual interest. Just to illustrate this, in 8th grade, one of the most exciting weeks of my life was 8th grade spring vacation. The day before spring vacation, on Friday, my 8th grade teacher brought me the Algebra 2 book from high school. I'd been waiting for that for weeks. He brings me the Algebra 2 book, and I was so excited. Every morning, afternoon, and evening throughout the week, I was doing that Algebra 2 book, so that at the end of the week, I brought him back a stack of papers with every problem solved in the Algebra 2 book. So in that 9 days, a week plus a weekend, I was able to complete the full year of Algebra 2 in high school. It was tremendously exciting to me. I loved it. I loved math. Naturally, when I went to college, which was Wellesley College, I majored in math. Now, science was different. Science, I really liked science fine in school, but I wasn't at all excited by it. And basically, the issue there was the science in grade school that I went to, it was taught as a finished product. And so I was supposed to learn what the teachers taught and what the book showed, and then I was supposed to spit it back on the exams. I was a very obedient child, and I learned very quickly how to proficiently do exactly what they wanted, learn what the book and the teacher said, and spit it back. But it wasn't at all exciting. when science became exciting to me was actually through the history of science. And it happened with one particular problem that arose when I started to think, it was the summer after my junior year in college, I started to think, how in the world did people figure out that the Earth is going around the sun? Now, I'd been taught that since a very young age. I certainly knew it was true, but it occurred to me that it really is so non-intuitive. There's no way it feels like we are spinning through space at this huge, rapid speed, and there's no way that it looks that way. So the senses tell us that this is not true, and yet I knew that they figured this out before telescopes, and it just bothered me that I didn't know how they figured it out. So I went to the MIT library to find that answer. And by the time that I found that answer, which was pretty quick, the reason is the orbits of the planets around, through the constellations, in particular Mars, which is going through the constellations really nice in one direction, then it stops, and it goes back, and then it goes forward again. And it clicked. It clicked how they were able, through those observations of Mars and a little bit of intuition, to say, oh, you know, this will work better if you change the center to the sun. And so it was through that, and then I started getting excited about science, and I started thinking, well, how'd they figure out things like the composition, chemical composition of the sun? And I knew that it was mostly hydrogen, and then next was helium. But in school, that's what I learned. You know, I learned the chemical composition of the sun. And then when I started asking, how did they figure that out? That's when science came alive for me. So it was late in terms of, it wasn't until the summer after my junior year in college that I really got excited by science. Now, by this time, even though my prime excitement was still math in terms of anything intellectual, I knew that I wasn't going to end up being a theoretical mathematician, which is where my heart was, which is where my love was. I loved the math, did well in the math, but I knew I couldn't go into it. And the reason that I couldn't go into it ends up because despite the fact that my time and my energies were so devoted to schoolwork, I knew, always knew, that the schoolwork was not the most important. I knew that what I was learning at home and in Sunday school and church that seemed so obvious and therefore really didn't take any time because it was so obvious, I knew those things were more important. And those things were things like be kind to people, be fair to people, don't lie, don't steal, don't use foul language, and certainly don't kill. The problem was I looked at the world around me, and in looking at the world around me, there is no way that the world around me was matching those ideals that seemed so obvious. And the two huge social political issues of the day, the civil rights and the Vietnam War. It is quite clear in the civil rights case, people were not being treated fairly. No, by no stretch of the imagination could people say blacks in this country were being treated fairly. And in the Vietnam War case, there was no question but that there was massive killing going on. Not just killing, but also the huge unfairness of the fact that the draft that existed at that time, every male of my age group had to deal with the draft. Because I was female, I didn't have to. Half the population had to deal with it, the other half didn't. And this seemed incredibly unfair. So even though my time was devoted to my schoolwork, I couldn't ignore these two major issues. And in not being able to ignore them, this had huge impacts on my career. The first one I've already referred to, which is it got me out of theoretical math, which is where my heart really was in terms of intellectual interests. So it got me out of what I really was most attuned to, the theoretical math, and that was partly because I really got concerned, what if I develop a theory or equation that ends up being used to build a better bomb or do something other nefarious things like that. A second impact was I did get quite substantial amount of press coverage over the years, and a lot of the articles ended up saying things that weren't true. This made me very wary and hesitant regarding the press. And so it's certainly, for much of my early career at Goddard, there is no way I ever wanted to talk with the media. And then also, third, in terms of a huge impact, I did end up in jail for 20 days at the end of my college career, and this meant that it certainly impacted a lot of things for me. I was told at the time that people could not understand how I could have been so stupid that this would ruin the rest of my life and that I would never get a meaningful job. This had pluses and minuses for me. The next 2 years, it was hugely difficult for me. The next 2 years were probably the toughest years of my life. I did not get a job easily. The job that I finally got after months of trying was a half-time job, and I never had more than a half-time job for those 2 years. So it was very tough on me, but there were pluses, and the pluses come later. It did mean once I did get a meaningful job, my golly, that meant a heck of a lot to me. During that next 2 years, I did end up having a lot of free time because I never had more than a half-time job. And so I did end up writing my first journal publication. It was in a math journal. And for those who aren't mathematicians, there's a subfield of math called group theory. And I came up with some new results about a particular characteristic of groups called ambivalence. So also, however, by the end of those 2 years, in fact, well before the end of those 2 years, it became clear that the grant that I was working under for the part-time job that I did have, that was ending up being ended in a couple of months. So I had to think of what else to do, and I certainly didn't want to go into the job market again, which was just too discouraging, getting rejected and rejected and rejected. So instead, and I never really blamed that on the jail sentence. It was a bad economy at the time, and I was very lacking in self-confidence, so I was not good in interviews. So I never really blamed the difficulty of getting a job exclusively on the jail sentence. But still, it was a tough 2 years because of not getting a job. So I went back to the library and tried to think through what I could do. And I ended up deciding I would really like to go to Antarctica. And there were some pluses to going to Antarctica. First, it was cold, and I always liked cold weather, which was kind of energizing to me. And in addition to the cold, it's also kind of isolated, and this appealed to me. But in addition, there was also this phenomenal Antarctic Treaty that was signed in 1959, so I knew about it in grade school. A phenomenal treaty saying that Antarctica shall be used for peaceful purposes only, where all the major countries of the world came together and said, this entire continent, we're going to do peaceful, cooperative research. And this was just tremendously appealing to me. So I decided I really would like to go work in Antarctica. So back to the library to figure out how in the world do I get myself to Antarctica. And the place that kept coming up was the Institute of Polar Studies at Ohio State. It was clear that they sent a lot of people to Antarctica. So I wrote a letter to the director of the Institute of Polar Studies. I explained my background, which had nothing to do with Antarctica, but I gave him the information about my academic record, which was very good. It was just not relevant to Antarctica. And I was suggesting that maybe for a year or so, maybe I could study up, and if I could be like an assistant on their on an expedition, maybe I could eventually become a graduate student. Well, Ohio State accepted me as a graduate student on the basis of the academic record. They actually never asked the question about a jail record, so. So I ended up going to Ohio State. And indeed, a year and a little bit more later, I ended up successfully getting down to Antarctica. And I got to Antarctica because of this individual here, Terry Hughes. Terry Hughes was leading an expedition to Antarctica. He knew that the only reason I went to Ohio State was to get to Antarctica. And so he got me on his expedition. Not only did he get me on his expedition, and all the expeditions to Antarctica field work in the U.S. Was funded through the National Science Foundation, NSF. And so he was funded through NSF. NSF sent me a letter of rejection for me to be on this expedition. And when I got that letter, I totally understood. I felt it was entirely my fault. I had passed out during the physical, which was not good timing at all. So I felt my fault and was terribly discouraged. I went to Terry. I said, Terry, if I can help from here, I'd love to, but NSF has rejected me for the expedition. And Terry said, well, can I see that? And I said, yeah. And he said, do you still want to go? And I said, well, of course I still want to go. And he said, he looked at it and he read it through and he said, Claire, if a male had passed out during their physical, we would have laughed at him, but he would be going on this expedition. You're being rejected because you're a female and we're going to fight it. And he did. And NSF quickly changed their minds and let me on this expedition. And I'm very pleased to say that the program manager at NSF, who funded this expedition of Terry's and approved for me to be on it, is sitting right here in the audience today, Dr. H.J. Zwally. So it was thrilling to get to go on this expedition. I was the only female on the expedition. I was the only female on the ship going down. I was the only female on the island that we were doing the study on it on. But it was thrilling to go. I got to see wonderful scenery along the Antarctic Peninsula, got to wander amongst the penguins and the elephant seals and lots of other wildlife. But most important was that I got to participate in a scientific expedition. And this expedition, again led by Terry Hughes, this expedition was regarding a crater that had recently erupted. It's a volcanic island, Deception Island, right off the coast of Antarctica. A crater had recently erupted, and the ice that had been on top was slowly coming back into the crater. So what Terry had us do was measuring this ice flow back into the crater, and this was all a pilot study on the stability for a bigger project on the stability of the West Antarctic ice sheet. Terry was way ahead of his times in terms of realizing the importance of this region of Antarctica, West Antarctica, in terms of the stability being much less stable than the bulk of Antarctica called East Antarctica over here. And so it was very exciting to be a part of this expedition. Unfortunately, Terry then, shortly after, decided he would go to the University of Maine. He asked me to come along as a graduate student, but I was very reluctant to leave Ohio State, which had accepted me as a graduate student, go someplace else where all the requirements might be very different. So I decided I would stick it out at Ohio State, even though I would have loved to be working on the stability of the West Antarctic ice sheet. So then I was left not knowing what to do a PhD dissertation on. And then a wonderful piece of luck came along in terms of this individual, Warren Washington, from the National Center for Atmospheric Research, NCAR, in Boulder, came to Ohio State to give a talk on what we would now think of as global climate modeling, but at that time, only the atmosphere was included, so it was called general circulation modeling. So Warren came to give a talk on that topic. I had never heard of Warren Washington. I had never heard of NCAR. I had never heard of climate modeling or GCM modeling or computer modeling at all. But when Warren gave his talk, I was sitting there thinking, my golly, this is exciting, what they're able to do with a computer to simulate the global atmospheric system. And so I got the nerve up, and it was the first time in my life I ever got the nerve up to go speak to a speaker after his talk. But I felt this was really important to me because I felt here's an area where maybe I can use more of my math than I was able to use so far at Ohio State. So I went up to Warren afterwards, and that conversation that we had was a wonderful conversation, and he ended up getting me to NCAR for that summer. By the end of the summer, Warren and I and my advisor at Ohio State had all decided that a phenomenal project for me to work on for my dissertation would be to develop the first global model of Arctic and Antarctic sea ice with both dynamics and thermodynamics in it. And so I wrote a proposal to NSF to do this, and then I went back to Ohio State for a year to finish my coursework, but the end of that had been funded by NSF, and so I got to spend 2 years at NCAR doing the research to develop this model. So the model I finished in, I got the degree in December of 1977, and then NCAR published it as an NCAR cooperative thesis in a few months later. However, before it came out in September of 1977, I went to a conference in Seattle to present the results from the model. And it was at that conference where I presented the results that another huge bit of luck came along, and that is this individual, Jay Zwally, heard my talk and came up to me during the break afterwards, and he said, Claire, do you know what you're going to do after you get your degree? And I said, no, I've been so busy working on the dissertation, I really don't know what I'm going to do. And he said, well, what would you think about working for NASA? Never in my wildest dreams had I ever thought that I could conceivably work at NASA. Back in the 60s, when so many bad things were going on regarding civil rights and the Vietnam War, one shining light was NASA and its Mercury and Gemini and Apollo programs. And especially the landing on the moon in July of 1969, when they placed that plaque, "We came in peace for all mankind." To me, that was just so amazingly the most important moment in terms of making me proud to be an American during that very difficult decade. NASA had done such incredible things in terms of technologically getting us to the moon, and then to have those words, "We came in peace for all mankind," just capped. And so when Jay asked me, how would you like to work for NASA? There was just no question but that it was just sky high, my top choice of where to work. So the application process, as those who have gone through it know, takes a while. However, I did successfully get to NASA then, started in July of 1978, and have been here for the past 34 years. When I got here, I quickly met Dave Atlas, who was the head of the large laboratory here doing lots of research. And Dave had a wonderful vision of, we have satellites, basically new satellites up that are collecting all sorts of data, and all this data is coming down, and we need people to figure out how this data relates to the Earth. And so he had groups looking at vegetation, groups looking at sea ice, groups looking at snow cover. He had groups just trying to figure out how do we make sense of the satellite data. And so I was in the group on sea ice led by Jay, and we were looking at passive microwave data from the Nimbus 5 satellite. The acronym for the instrument is the ESMR instrument. And we were getting data that looks kind of like this. So all the black is missing data. Today, the data are so much better that we get than versus what we were getting back at that time. However, at that time, this was brand new. Getting any data at all on the global coverage of sea ice was brand new. So we were seeing things before anybody else had seen them from the satellite perspective. It was an incredibly exciting time at Goddard. And so we took these data, and it turns out we had a much easier problem than the people trying to determine snow cover, because there's such a big distinction between where the sea ice is and where the ocean water is, because sea ice and oceans and liquid water simply emit very differently in terms of the microwave. However, the instrument was a first proof of concept type instrument. Wonderfully successful instrument, but nowhere near the quality of what we can get now. And it had only one channel on it. In the Arctic case, a lot of ice remains in the summertime. And so that produced a problem because we only had one channel of information. The ice that remains in the summertime ends up getting melt ponds over it. It changes the microwave signal, so we really needed more than one channel to get the information that we wanted. In the Antarctic case, it was somewhat simpler because overwhelmingly more of the ice ends up retreating in the summertime, so you don't get this so-called multi-year complication anywhere as near as much as you do in the Arctic case. And so we addressed the Antarctic first. And addressing the Antarctic first, we would take a map like this, and that map converts to this map. So in other words, we took that one channel of information, we converted it into one bit of information, which is for every pixel, we plot the so-called concentration of the ice, which means for the pixel, it's what fraction of that pixel is covered by ice versus water. You notice that there's this big area here called a polynya, an open water region in the midst of an ice cover. And 3 of the 4 years of the ESMR data, we had 4 years of ESMR data that we were trying to use and compile, 73 through 76. And 3 of the 4 years, you had this big open water region. And so a lot of people were doing studies trying to figure out what could have caused this. And I used my sea ice model, and I did a little study on the winds being able to generate this kind of situation and its decay. Other people looked at the issue of the impact of oceans. And however, this particular image, so keep this one in mind now, that particular NASA image of ours did end up in the Globe tabloid, and they had a different analysis. So there are different analyses here. Actually, did make some sense to it, because after all, this open water region, there must be some sorts of heat to generate it, and so their analysis was a UFO. Clearly, none of us here at Goddard actually accepted that particular theory, but we continued with the analysis of the data, and in 1983, led by Jay, we got the Antarctic Atlas, which was a book compiling this data set from the ESMR, the 4 years of the ESMR data, and we completed that in 1983. We then turned to the Arctic problem, and I took the lead on the Arctic case, and that ended up published in 1987. 5 people were on both of these books. Those 5 people are Jay and me, Joey Camiso, Per Glorson, and Bill Campbell. And then each of the two also had one more person. In the Antarctic case, it was Frank Carsey, and in the Arctic case, it was Don Cavalieri. So all of those people heavily involved in these two products, which really were kind of state-of-the-art and first satellite atlases of sea ice cover in the Arctic and Antarctic. In the Arctic case, as I said, there was a problem because of the multi-year ice. And so we had to go with a solution that none of us was entirely happy with, but at least we had some solution that would get us results. We would much rather have had a single scale here. And we were very, very pleased that each of the subsequent instruments didn't require this so-called nomogram. This is the fraction of multi-year ice. And so in order to figure out what the concentration is, you have to know the fraction of multi-year ice. And so it's just much more complicated than what we would have preferred. So we were very happy that all the subsequent instruments end up having more than one channel. And it allows us to sort out that problem of the sort out the multi-year and first-year ice problem. So the subsequent instruments, the Simmer on the Nimbus 7 satellite, which was launched in 1978 in October, and then that died in August of 1987. Fortunately, by that time, just a couple of months earlier, a different instrument had been launched by the Defense Meteorological Satellite Program, DMSP, the SSMI instrument, and the SSMI and then a little advanced version called an SSMI Sounder or SSMIS. Those have continued to be launched so that our record of what we use now is generally the Simmer and the SSMI record. Then in 2002, JAXA, the Japan Aerospace Exploration Agency, has an AMSR-E instrument on the Aqua satellite. And this has been wonderful. The JAXA instrument actually has greater spatial resolution. This picture is from the JAXA one, greater spatial resolution than the previous instruments. So we were able, after the ESMR data, with all the subsequent instruments, we've been able to get a single scale of ice concentrations, which is much better than to have that more complicated and cumbersome nomogram. So by the time the atlases were done, and the atlases consumed a huge amount of time, but by the time they were done, we had a much longer record from the Simmer data. And so Don Cavalieri and I, in 1989, we published this result that showed that although we had this huge gap between the ESMR data and the Simmer data, it did show that in the Simmer years there was this slight decrease. Now, given the interannual variability, given how short the record was, there really wasn't much to say other than that there's a slight decrease in terms of this topic. But we knew that with global warming anticipated by a lot of people by that time, we knew that this was something to at least keep track of. And so we, as a group, kept track of this. And in 1999, after a lot of work to try to match the data sets, the Simmer data set with the SSMI data set that came after, when we finally got this compiled and we were able to produce this result, much longer data record, and a much clearer suggestion of decreases in the ice cover. Now this shows month by month. Month by month, there's so much more ice in the winter than the summer that the seasonal cycle dominates in terms of what you can see. However, when you take the seasonal cycle out, which is what we do with these monthly deviations, then you can see the long-term trend. This paper came out the same year, 1999, when another paper came out from the University of Washington, who used submarine data to look at the thickness of the sea ice cover. And so these two papers coming out about the same time ended up generating some media interest because of the fact that both of them were showing a decay in the sea ice. So the NASA data with the satellites was showing a retreat of the sea ice in the Arctic, and the submarine data from The University of Washington efforts led by Drew Rothrock was showing a thinning of the ice. And so this got some considerable press coverage, and really after this point, things changed a lot because suddenly lots of people were interested in the Arctic sea ice cover. Now you can see it's not entirely convincing still because some of the highest values end up in the last year of the record at that point. We only went through 1999 at that point. But it was clearly a downward trend. A lot of people became interested, and not only because of the fact that it was showing a signal that certainly seemed to be related to warming, also the fact that computers had advanced so much, satellite instruments had advanced so much, it was so much easier to deal with the satellite data. When we started with Jay and others back in the late 1970s, when we started this effort, there was almost nobody else in the world was looking at the satellite data. It was so much more difficult to deal with the data at this time, and certainly nobody had desktop computers to help them out. Well, now people on a desktop computer and with the internet can go get this data and easily plot their own plots on it. So it became not just scientists, many more scientists looking at it, but also the media. The Arctic sea ice has become one of the kind of poster childs of the global warming issues. And so we've continued to update these plots, and these are two updates from me and Don. One went through 2006, and showing that the decay in the Arctic ice cover was clearly accelerating. And the other just published this month and goes up through the end of 2010. And it shows that there's a huge plummet after this in 2007 when the Arctic ice cover reached its low point, and was just amazing to all of us to see this plummet the way that it did. Then fortunately, in the next couple of years, it came back up a bit. Unfortunately, it looks like there's very likely going to be a new record low. This is from our website. It's actually Joey Camiso and Rob Gersten who do the bulk of the effort to make sure that this is updated every week. And so this is an update from a couple of days ago in terms of the Arctic sea ice cover. So this black line, you can see that the black line, things were looking pretty good in the springtime, but then it's really plummeted. And the big influence here could be a storm that some of us are working on trying to analyze right now. We do the same studies with the Antarctic. And in the Antarctic case, of course, the seasons are exactly the opposite. February is the summertime. Again, huge seasonal cycle. So we take out the seasonal cycle. This time, we take out the seasonal cycle, and it's an increase instead of a decrease. So it's very different from the Arctic case, and does not fit anywhere near as nicely into the thoughts about global warming, although a lot of effort is being done to try to analyze why the Antarctic ice is increasing, and there are some reasonable explanations. It's not just increasing overall. Every single month it's increasing. So Januaries are getting more ice, Februaries are getting more ice. Every month of the year has increases. And we do same thing on our website in terms of keeping this up to date. And the values this year are a little bit higher than they had been. So Antarctic ice increasing, Arctic ice decreasing. We certainly do a lot more than just trend studies. And this is just one example that Joey Camiso and I published showing sort of some of the hardcore work of trying to match data sets. And in this case, we were trying to match two different algorithms that are both of which are used here at Goddard, one called the bootstrap algorithm, one called the NASA Team 2 algorithm, and trying to match also different instruments, the AMSR-E instrument and the SSMI instrument. And we find that whichever algorithm you use, whichever instrument you use, the results come out pretty close, which was encouraging. We certainly wouldn't have wanted it otherwise. But the key is here in terms of the results. Arctic ice, very significant decrease. Antarctic ice, somewhat lesser of an increase. Both of these start with the beginning of the Simmer record, which is in, essentially November of 1978. Simmer was launched in late October of 1978. The Arctic case, much bigger magnitude trend here. The Arctic case has certainly been mentioned many times in the context of global warming. So now I turn a little bit to this issue of global warming. It's well known that humans are having an impact. It's well known that we pour massive amounts of material into the atmosphere and into the oceans, and it's well known that the population has skyrocketed and industrialization has increased. It's thought from all the increases in especially carbon dioxide that this will warm up the climate. In terms of the record of temperatures, there's clear record of warming over the period since the late 1800s. However, it's not uniform. There are decreases here, especially between 1940 and 1970. Now, if you recall, in the 1970s, mid to late 1970s, I did spend 2 years at NCAR working on my dissertation. Now, at NCAR at the time, there were a lot of scientists there, and I had lots of conversations with them, people like Steve Snyder and Bill Kellogg and Warren Washington, and all of us felt that even though temperatures had been decreasing, that the theory was pretty sound in terms of the climate was going to be warming because of the increase of greenhouse gases in the atmosphere. Greenhouse gases being gases that allow sunlight to get in easily but block some of the Earth's radiation from getting out. So it was well known amongst climate scientists at that time, despite the fact that there had been cooling, despite the fact that some people were mentioning a possible coming ice age, it was well known amongst the climate scientists that very likely there was going to be a warming that was going to be very much more than the fear of the cooling. And so I did a study with Will Kellogg, and we used my little sea ice model in order to see what would be the effect on the sea ice cover of the warming that we were anticipating in the Arctic. And so we ended up in this study determining that with the 5K warming in the Arctic, that we would have an ice-free Arctic in August and September. This is a July image here, so it shows that the Arctic ice really decays quite a bit in July versus the standard case. So this is the standard case over here, and then the expectation of a 5K warming, approximately what you would expect at that time from a doubled CO2. So I was... This, in fact, as far as I know, was the first paper that actually modeled the impact of CO2 increases on anything other than temperatures. So I was an early convert to the fact that we've got some concerns over global warming. However, all along, I've also looked at the data, and I realized that the data are not like 100% in just one direction. And this is a really telling example here of why I'm more cautious than some of my colleagues, even though I'm firmly in the mainstream on climate warming issues, why I'm more cautious than some. This plot was published in a paper by George Kukla and Joyce Gavin back in 1981, and it shows a huge decrease in Antarctic sea ice coverage. Washington Post at that time announced that this could be the first geophysical evidence of global warming. This was early on, 1981, in terms of concerns about global warming. Well, by the time this paper came out, Jay and Joy and I realized that this trend had already reversed. And so we published a paper in Science in 1980 that came out in 1983 that showed, yeah, it had been decreasing, but then there was this increase. And as I showed in the previous plots, increases have continued. So the Antarctic case really did caution me against jumping to conclusions too quickly. And also, if we look at the Arctic in the 1999 publication, the region that showed the sharpest decrease was the seas of Okhotsk in Japan. Huge decreases there. However, you add a few more years of data, and those huge decreases were reversed to increases. Another reason for some caution, and even when you take the Arctic as a whole, if you stop it at 2007 when we had that remarkable decrease, I mean, this looks really, really serious in terms of a plummeting of the ice cover. And yet, in the few years since then, it's gone back up again. But as I showed in the previous plot with an update from our website, it goes down. So there's still huge concerns about the Arctic sea ice. So to summarize my views on this particular topic, I am firmly in the mainstream, and it's greenhouse gases. Clearly, we're increasing them through humans. The theory on greenhouse gas influences on temperatures is very solid, and there's quite a bit of evidence for warming, both temperature records and related changes such as the sea ice cover and things happening to plants and things happening to various animals. So there's a lot of evidence firmly in the mainstream. Reasons why I'm not 100% sure are the Earth system's really very complicated. And yeah, greenhouse gases cause it to warm, but greenhouse gases aren't the only factors that are influencing climate. The models are not perfect. The models are human-built, and we surely don't have everything in them yet. And so the models are imperfect. My background in math and my inclinations for math, I know with math when you've really proved something, and it's quite clear we can't prove what's going to happen in the future. So that automatically makes me a little more cautious than some people whose background is not mathematical. My history of science background. History of science, theories that are solidly agreed to by the whole community end up getting overturned in scientific revolutions. So just because it's a big consensus doesn't mean it's right. Although, again, I am in the mainstream here. So even though I'm listing some issues, people issues in terms of there is peer pressure to agree, and some of the records don't indicate as strong a warming, like the fact that the Antarctic sea ice doesn't indicate the same thing that the Arctic sea ice does. Key reasons why I advocate a balanced picture. Certainly, to me, it seems the wisest, most reasonable, most honest route. Certainly, it seems to me that it's got the best chance of effective action. And I think that some of the antagonisms that have been generated over this issue of climate warming have really, really harmed getting effective action on the issue. And I think almost all of us feel that we would like some more effective action than what we're getting. But I knew that there's a lot of nastiness on this issue, and I was happy to just kind of avoid it and spend my time on things that were real positive that nobody was really objecting to, things like this book on just showing people how to use satellite imagery, or this book, Our Changing Planet, done with Michael King and many others, on look at all the spectacular, wonderful things we can see about the Earth from space. These are hugely positive, gets me away from the contentions in the climate warming debate. So I was very happy to be doing this kind of thing instead. What changed, and why I felt I needed to speak out on the other topic, was in came up because of geoengineering. Geoengineering, for those who aren't familiar with it, geoengineering is the attempt to somehow engineer the climate system. And there's some possibilities that are actually good. And most geoengineering schemes that are talked about now are specifically aimed to lessen the global warming problem. Some make total sense. Artificial trees to suck out some of the carbon dioxide that we put in, I mean, that makes sense. You know, take some of it out. If we put it in, okay, take some of it out. Reflective surfaces on roofs. Sure, paint your roof white and reflect the sunlight away, and you won't need as much air conditioning in the summer. This makes sense. This is okay. However, some of the other schemes are, instead of reflective surfaces on roofs, put reflective surfaces over the entire Sahara Desert, put reflective surfaces over a huge portion of the Pacific Ocean. Now, this makes a lot less sense because you're going to be destroying the entire ecosystem of these locations. So some make more sense than others, and one of the ones that has gotten most attention is pouring aerosols into the atmosphere. And my feeling, and I hope I didn't really need to say this at the beginning of the talk because this is a Goddard audience, but of course, anything I say that's related to policy, that's me as an American citizen, not as a NASA scientist, so get that little qualification out. So the concept of pouring aerosols into the upper atmosphere comes about because it's well known that when a major volcano erupts vertically and gets a lot of material into the stratosphere, this has an impact on temperatures. On stratospheric temperatures, there's a huge increase in temperature briefly, but on tropospheric temperatures, the temperatures that people talk about in the context of global warming, on tropospheric temperatures, it has decreases. So when Mount Pinatubo erupted, indeed, Jim Hansen almost immediately said, yeah, it's going to be cooler next year than our predictions had been before this eruption because we got all this material in the atmosphere that's going to be reflecting away some of the solar radiation and absorbing some of it and lessening the amount that gets down into the troposphere. So people realizing that pouring all this stuff from a volcano into the upper atmosphere cools things have come up with the thought that, well, maybe we could do this ourselves instead of waiting for a volcano. And so they actually have come up with lots of calculations on how much stuff to pour into the atmosphere. And my feeling is our damage is because we've poured things into the atmosphere. I don't think the solution is to pour more into the atmosphere or the oceans. But the key thing in 2006 that happened that got me to feel I had to say something, even though what I say really doesn't matter much, but just sort of for my conscience, I felt I had to say something, was this paper by Paul Crutzen, who's the Nobel Prize winner. And although he made it very clear in his paper that the preferred option is to reduce the input of carbon dioxide into the atmosphere, he was taking seriously and did say that the rest of us should take seriously this concept of the so-called artificial volcano by pouring material into the stratosphere. When I saw that and I realized that this is no longer something that previously I had heard these schemes and just thought, I can ignore this because surely nobody's going to do this. But I could no longer think that when a Nobel Prize winner was saying this. And so I ended up, within a week of reading his paper, I had written a proposal to write a book on that then came out in 2010 that deals with the coming climate crisis, and I go through the history, the Earth's history, and I go into concerns about geoengineering, and in order to get the complete story in there, I did have to put things in my context about global warming itself. And even though it's clear I'm in the mainstream, I did realize that some people in the mainstream were going to be upset with me because I do not denounce the skeptics. And indeed, some people have been upset with me for not denouncing the skeptics, but I've been very pleased that a lot of people have specifically told me how much they appreciate that I didn't denounce the skeptics. And this includes a lot of people in the mainstream. So this was the first book that I ever wrote where I was nervous about its coming out. Every other book, I've always been thrilled to get it out and anxious to get it out. This one, I was nervous about getting it out. And now, two final slides that simply say something about this other project that Charles mentioned in the introduction, which is that I'm project scientist of this mission called Aqua. And I've been project scientist since 1993. This being project scientist takes a heck of a lot of time and takes a lot of time away from research. However, this mission has done so much that is so positive, and even though it takes a heck of a lot of time away from research, it's been really very it's been a privilege to be able to be involved in a mission and play my little role in a mission that does so much for humanity, including like over 2,000 publications have come out in terms of science publications. So that's a huge plus. But then also the practical applications of the mission, like being able to see fires so well from the MODIS imagery. With the Aqua Mission, I feel unquestionably that I do have a job that is meaningful. And that gets me back to the comment back in 1970 that I had destroyed my life and would never have a meaningful job. My job, I feel, my job and everybody's job in here who works for NASA, everybody's job is a meaningful job, even though a lot of times we have to spend a lot of time on ridiculous exercises. We do have meaningful jobs, and every day for the past 34 years, I've appreciated NASA for giving me this opportunity. Thank you.
We can take one or two questions. Yes, Jim.
In the interest of fairness and open discussion, I've got a question for you. So we know that melting sea ice will not change sea level, so that won't be a problem. So aside from polar bears losing their habitat, what is bad about losing Arctic sea ice?
Okay, Gene, thanks a whole lot for asking that question. The Arctic sea ice is white. White means that the sun's radiation that comes down and hits it gets reflected off. When the Arctic sea ice retreats, the sun's radiation that would have hit this white surface and get reflected off instead hits the liquid water. Hitting the liquid water, it gets absorbed in. So as the Arctic sea ice retreats, more and more of the sun's radiation that would have gotten reflected off gets absorbed in the system, compounding the warming issue. So for that reason, it's important. In addition to the polar bears, there are a heck of a lot of other animals in the Arctic that are hugely affected. Arctic foxes, and they're little organisms that live within the sea ice. And so all the way up and down the food chain, life is affected. But the climate impact is huge, too. And in addition to the reflection issue, the Arctic sea ice is a huge buffer between the ocean and the atmosphere, and that goes away when the sea ice disappears.
Okay, Bob?
Well, let me first say it has been a pleasure, as Charles said, have you out of jail the last...
Thank you. Thank you.
Have you there so that when things are happening, we know to come to someone we can trust to interpret it for us. So thank you very much.
Thank you.
It's been wonderful.
Thank you.
In terms of the uncertainties and sort of where we go from here, one of the things that worries me about the models is that we know the biggest forcing is from that, increasingly the big forcing is that population growth that you pointed to and humans' energy use per capita. And right now we take these sort of scenarios of what humans might do, and different scenarios lead to very different outcomes. And also a lot of the CO2 is going into the oceans, particularly in the Arctic where it's cold and the CO2 uptake is fairly high. What are the prospects for getting biology into these models and sort of forecasting what might happen to the biology? This is a horrible question, but you know, and how it might affect climate and how climate might affect the biology and how those two things interact with each other. Is there work going on that?
There is certainly work going on some of the biology, like the vegetation cover. There's certainly work going on there. Since I'm not a biologist, if there's anybody in the room who can actually answer that question, I'd love to defer to anybody who's maybe able to. Okay, apparently not. But anyway, there are certainly efforts to get...
research opportunity.
Okay. There's certainly efforts, and certainly in terms of the land vegetation, those efforts have been going on for, well, since the late 1970s. Some people have been working on that, I think Bob Dickinson is one who was one of the early ones to try to get some biology into these models.
Dyson is another.
Okay.
How about for the ocean where some shelled creatures can't form anymore, from what I hear, at least in the Arctic?
Okay. We need an ocean marine biologist here.
How the changing biology in the Arctic Ocean could feedback on Arctic climate. Sorry, I'm asking too hard.
Okay, no, that's fine. I'm just not sure in terms of the biology. We need biologists here, but I am sure that the whole trend toward computer modeling of the climate system has been to add in more and more variables. So I'm sure that eventually it will come.
Yeah, last question.
Claire, was ESMER originally designed to study sea ice? I actually have two. And then did you ever make it back to Antarctica?
ESMER was not originally designed for sea ice. ESMER was designed for passive microwave observations of the globe, and we were looking at sea ice, again, under J, and it turned out to be fantastic for sea ice. But there were other people looking at other variables, and the passive microwave has proved valuable for some of them too. But sea ice was as perfect a choice for the passive microwave as any because of that huge contrast between the emissions of the ice versus of the background liquid water.
And back to Antarctica.
And then, no, I didn't go back to Antarctica, but I've been studying Antarctica, so I feel like I'm still part of this Antarctic Treaty effort anyway. Yeah, and that slide sort of showed other expeditions. I went to the Bering Sea and the North Pole, but not back to Antarctica.
Okay, let's thank Claire one more time.
Thank you.